We're going to look at an effect now called aliasing. Now we touched on this in a previous video when we looked at the discrete time Fourier transform. So we'll go through a kind of similar process here. Let's say we've got a function g of t and we're going to multiply it by this impulse train in the time domain, that's s of t. So this impulse train, the period of this impulse train is going to be t naught. So each of these are separated by a value of t naught. So whenever we multiply these two together and we convert it to a discrete time signal, we're going to get this function g of nt. So this is our sampled function. So we've seen that before and there's nothing new in that. Now if we were to take the Fourier transform of each of these, well, we'll take this Fourier transform of this g of t and let's say it gives this function g of I omega. Now this g of I omega, it's not band limited, so it could go on for a large distance here in terms of the frequency axis. Now we've seen as well, whenever we Fourier transform our impulse train in time, it gives us an impulse train in frequency, and the impulse train in frequency is going to be separated by a period which will be a value of omega s. And this omega s and the t here are related because omega s equals 2 pi upon the t. Now there's another thing here that I'm not going to prove here, and it has actually been proven in the Fourier and Laplace transforms course, and that is that if we were to multiply two functions together in the time domain, it's equivalent to convolving them in the frequency domain. So what we're going to do is we're going to convolve these two functions. Now another thing that is not proven here but is proven in the Fourier and Laplace transforms course is that if we were to convolve this function with an impulse train, it's equivalent to taking the function and just replace centering it at each of the impulses. So that's what I've done below. We've convolved this by simply taking this function and recentering it at omega s and minus omega s. So you can see here, this function here is g I omega. Now I've called the function at the bottom, it's g I omega, but I've put this little hat above it. It really tells us that this is the periodic function which we get whenever we do the discrete time Fourier transform, because that in effect is what we've got here. We've sampled the function in time, so it's now a discrete time function, and then we've Fourier transformed it, so it's the discrete time Fourier transform. Now you can see the effect of aliasing here, and again this was alluded to whenever we looked at the discrete time Fourier transform, is that this signal here, part of the higher band here is going to impinge, or it's going to mix with the lower band of this part of the signal, and again with this part here and this part. So it means that whenever we look at the actual discrete time Fourier transform, it's going to come up like this, it'll come down to there, and then up here, down to there, and up to there. So you're going to lose this part of the signal for this part here, and you're going to lose this part of the signal of this part of the periodic discrete time Fourier transform. And the loss of these parts of the signal are actually unrecoverable, meaning we're not going to be able to get back to the original function if we were to do an inverse transform. And this is the phenomenon of aliasing. So we can see intuitively here how we're going to prevent aliasing. In order to prevent it, we would have to make sure that the highest frequency content of this signal here can be at most half of this distance omega s, because if it was only half the distance, that would mean that, for example, this signal would come down to here, which in effect with this signal come down to this point here, and then the next signal would start from this point up to here. So it would mean that there wouldn't be any overlap between this part, and this part of the periodic signal. So let's look at this mathematically. So we start off with our function g of t, and we multiply it with our s of t, and we get our discrete function g of nt. So that's just as above here. So we've multiplied this function by this function, and we've got this function here. Now in the frequency domain, the multiplication is the same as a convolution. So what we're doing is we're convolving the function g of I omega with our impulse train in the frequency domain s of I omega. Now there's actually going to be a factor here of 1 upon 2 pi as well whenever we do the convolution in the frequency domain. Again, that's proven in the Fourier and Laplace transforms course. So this here is just the same as the right hand side of this graph here. So we've got our g of I omega times it convolved with s of I omega, and it's going to give us this function here, g I omega. Now I put the g a little hat on top of this g of I omega because this here represents, as I said, the actual discrete time Fourier transforms, and I've got the little hat there to make the difference between this one and this g of I omega here. Okay, so what we can do is, if we look at the right hand side of this, we're going to have this g of I omega equals 1 upon 2 pi g I omega convolved with, and now if we replace the s of I omega, so this is the impulse train in the frequency domain, well, we can write that in terms of a delayed impulse, and we can add up all of the delayed impulses in the frequency domain, and those delayed impulses are going to be delayed by an integer multiple L omega s. So we can write that as the sum from L equals minus infinity to infinity of delta omega minus IL omega s. Now then what we can do is and of course there's actually a factor of 2 pi there as well. So we proved that in a previous video when we were looking at the impulse train in the time domain and impulse train in the frequency domain. So the 2 pi cancels with this 2 pi here. We take our g of I omega inside the summation, and we're left with this here. Now whenever we convolve a function with a delayed impulse, as we mentioned, it's the same as taking the function and shifting it to they're centering it on that delayed impulse. So this whole thing here is just the same as saying g of I omega minus IL omega s. So this is just the function g of I omega, which is delayed by integer multiples of the L omega s from L equals minus infinity to infinity, and that's going to give us this g of I omega, which is our discrete time Fourier transform. So this equation here is this function here. And we'll go on to this on the next video, but we did mention that in order to prevent aliasing, what we have to make sure is that the original function g of j omega, I omega, is going to be equal to 0. That is, in effect, it's going to be band limited for all frequencies that are greater than a half of omega s. So we set that up here. For frequencies here that is greater than half of this omega s, so that's omega s upon 2. So all the frequencies above omega s upon 2, those all become a value of 0. So in effect it becomes band limited. So let's have a look at this, and the idea of aliasing will become even more prevalent whenever we look at it on the next slide. So there's quite a lot in this slide, so let's take our time and I'll talk you through what we have here. We have a function of time f of t, and this is like a raised sinc function, and whenever we do the Fourier transform of it, we get this function here which looks like a triangle. So what we're going to do is we're going to sample this at 3 different rates. So the first sampling rate is going to be given by t1, the second sample rate is t2, and the third sample rate is t3, and we're going to compare them. So all the way down this column here is the function of time, and then when we come along this column here, this is the Fourier transform of these. Okay, so this is the time domain, and that's the frequency domain. And then we do the same with T2. This is the time domain here, this is the frequency domain, and with T3 we say this is the time domain and this is the frequency domain. So I've added in the multiplications and the convolutions to see the processor working through. So if we take this impulse train here, we'll call this impulse train S1, and you can see the impulses are tightly spaced. It means that whenever we go onto the frequency domain, the impulses are going to be very widely spaced. And then we go and we look at the sampling it at another value T2, and you can see here that the impulses here are more widely spaced. So it means that the impulses in the frequency domain start getting tighter, that is closer together. And in the third one here, we've spaced the impulses further apart still. So you can see here in this one there's 1, 2, 3, 4, 5, 6, 7, 8. There's 9 impulses here, but there's only 8 in this one. Okay, so the impulses are getting wider and wider apart. So if they get wider apart in the time domain, they're going to get narrower in the frequency domain. And you can see this is the pulses getting closer and closer together. So whenever we multiply this function here with the impulse train, we get this discrete function f1. And again, whenever we do the same with the different impulse train here, we're going to get the value, the function f2, and again we're going to get the value f3, and each time you can see that the pulses are more widely separated in the time domain. Now when we multiply these functions together in the time domain, it's the same as convolving them in the frequency domain. So this is the convolution, which refers to the frequency domain. So when we convolve the function, it's equivalent to taking the function and placing it, or centering it at the value given by our, in this instance here, omega 1. So we take this function here and we place it at omega 1, and that's us done it there. So this here is a value of our omega 1. And we also have the central one left as it is, and we place another copy at minus omega 1, so that's our minus omega 1 there. And this continues on as a periodic function to plus minus infinity. Now we do the same thing with the value of t2. We take our function here and we place it at the centre it at the value given in this case by our omega 2, and this is their periodic function here. So this is this function convolved with this impulse train here. Now the thing to notice in this figure here is that the little two blue dots we've got here, well, the first blue dot here is just the distance omega L, and the second blue dot is going to be a value of 2 omega L, so that's just omega L times 2, which is this distance here. Now you can see that because these impulses are very tightly spaced, that means they're very widely spaced in the frequency domain, and in fact they're widely spaced enough such that the value of our omega 1, it lies outside twice the value of our omega L. So we can see we get this extra little distance here. So it means that whenever we go and we convolve this with this here, we're going to be placing this function at the centre here, and it means that we're going to have when we place this function down here, we're going to have an extra little distance between each of these parts of the periodic function. So if we ensure that the sampling frequency here, called omega 1, is greater than twice the highest frequency content of this signal, so that's the frequency omega L, this is 2 omega L, so we want to make sure that this omega 1 is greater than twice this frequency content omega L, and that will ensure that we don't have any aliasing, and you can see that effect here, and we can see that there's a definite distance between each of those. So this signal here does not impinge on that one, so there's not any loss of information. So if we look at our sampling frequency in a time domain which is given by T2, so it means that the samples are a little bit more widely spaced on this one here. So in fact we've spaced them out such that whenever we get into the frequency domain, we've got this point here at omega 2 and minus omega 2. And you can see here that again we have this first blue point which is our omega L, which is the highest frequency content of our signal, and this point here is going to be twice that omega L. So you see here that this omega 2 just sits on twice omega L. So it means that whenever we were to convolve this function with this function, we take this triangle and we center it at this value omega 2. So it means that this value omega 2 is exactly twice the highest frequency content of our signal. So again, that whenever we do the convolution here, we get this effect here. So again, there isn't any overlap between these signals. This one finishes at the exact same point that this one starts. So there's still not any aliasing. So finally, let's look at what happens when we go to a sampling period of T3. So the samples are even wider apart here. So if they're wider apart in the time domain, they're going to be narrower in the frequency domain. And you can see again here we have our value of omega L. So our omega L actually sits down here, just where this value omega 3 is. And the twice omega L is this point here. So it means that the sampling point here actually is less than twice the highest frequency content omega L. So it means we're going to have aliasing in this particular example. So we can see that whenever we convolve this function with this impulse train, we take the function and we place it at each of these spikes. And whenever we do that, we can see that there's going to be an overlap between them. So it means that the final signal we're going to get out is going to be a signal that just comes up and down like this here. And the lower bands here are mixed with the higher bands of the next part of the period, and so on and so forth all the way along. So we're getting aliasing in this example. And we're getting aliasing because the sampling frequency is less than twice the highest frequency of our signal. So that's us looked at the first 3 rows here. So let's look at the last 2 rows. Now what we're going to do in these 2 rows is we're going to reconstruct our function. So if we take this first one, for example, here at the T1, if we were to take this function here and we were to multiply it by a little square function, and the square function here is of period omega 1, so the distance between there and there is going to be omega 1, then we can see here that when we multiply these two together, we're simply going to be left with the original triangular function, which was f of I omega. Now if we were to go in and look at this in the time domain, we know that multiplication in the frequency domain would be equivalent to convolution in the time domain. So whenever we took our sampled function here in a time domain and we convolved it with the inverse transform of this square wave, now the inverse transform of this square wave is a sinc function, so that's a sinc function there. So whenever we convolve this with this sinc function, we're going to get this raised sinc function, which is our original function f of t. So we're able to recover the original function f of t from the sampled function f1 of n t1. So it shows us here that there's no aliasing and we're able to get back to the original function. So we do the exact same thing with our sampling period t2. If we were to take this function here and we were to multiply it by a little square function here, in this case the period of the square function is going to be our value omega 2. And so whenever we multiply these two together, we're just going to get the original function back, which is our f of I omega. And again, if we were to do that in the time domain, this little square function here would give us this sinc function here, and when we multiplied in the frequency domain, it's equivalent to convolving in the time domain. So we would be convolving this function with this function, and we get back to our original function of time. So finally, let's see what happens with our aliased function. If we were to take this function here, and then we were to multiply it by this little square function. Now the square function, again, the period is going to be this omega 3 in this case here. When we multiply these together, we're going to get this function here. Now this function here is not the same as the original function f of I omega. We can't get back to the original function f of I omega because of the aliasing. Now again, if we were to look at that in the time domain, if we took the inverse transform of this square function, it would give us this sinc function here, and whenever we convolve this sinc function with this raised digital sinc function, we would get this function down here, which again would be another type of sinc function. But this function here is not the same as the original function. The original function here is a raised sinc, and the new function down here is actually a sinc function. It actually goes down below the f of t axis. So you can see here that we have not reconstructed our original signal. We cannot get back to our original signal because of the aliasing. So we are not able to tell which function was sampled in order to generate this sample function f3. So this sample function f3 can be generated by sampling this one here at that rate, or it could be generated by sampling this one here at that rate. So it means now that we have an alias for this function, and in fact there's an infinite number of these aliases. So in summary, the sampling theorem tells us how we can avoid aliasing, and by avoiding aliasing we can ensure that a continuous function can be uniquely represented by a set of samples. It tells us that a band limited signal with the value f of I omega equaling 0 for all values of mod omega greater than omega L, it can be uniquely represented by its samples provided the sampling frequency omega s is equal to or greater than twice the highest signal frequency omega L. So why is this the case? Well, it's really down to four things that we looked at throughout this video. One of them is that an impulse train in the time domain will give us an impulse train in the frequency domain. Secondly, if we were to multiply two functions together in the time domain, it's equivalent to convolving the two functions in the frequency domain. And thirdly, if we were to convolve a function in the frequency domain with a set of shifted impulses, it's equivalent to taking the function and centering them at the impulses. And finally, if this shifted function was to overlap, then we would get aliasing. We can prevent this aliasing by following the sampling theorem. So that's all there is for this video. Thank you for listening, and I'll get you on the next video. Goodbye.